So this is where we find ourselves entering into the area of what I'd refer to as proper statistics. The title of this particular module is Estimation and Inference, and within that is the essence of what we're doing. Very big picture before we start off. What we're going to be doing, and this is what statistics is at its core, is we're going to be taking a sample which we can observe, we look at it, and we use that sample to estimate and infer what value the population parameters are likely to be. All right, so a sample tells us information about a population. That's the idea. So you could be interested in the income, the salary of CFA Level 1 delegates in your particular year. It's going to be difficult to ask all CFA Level 1 delegates what their salary is, to take an average, to get a population average, what we call mu, Greek letters for population parameters. It's going to be a lot easier for you to find a sample of CFA Level 1 delegates and take a sample mean. Now, right at the outset, I'm going to say this many times in this module, pay attention to the fact that the sample mean is not the same as the population mean. The sample mean is a random variable. It bounces around. Sometimes it's higher, sometimes it's lower, and it depends on the sample. The population mean mu is static, all right, and stays where it is. The problem is we can't measure it. Okay, you can't practically find the salaries of everybody that's sitting CFA Level 1. Okay, so we can't see that. We can see this, and on that basis we take samples. This is what statistics is. We take sample statistics in order to give us an idea about where population parameters are likely to live. And they're hard definitions, by the way. Populations have parameters, which are Greek letters like mu, mean, sigma, squared variance, and it's samples that have statistics, like, for example, x bar, the sample mean, and s squared, the sample standard deviation. Okay. So the hit list here, we talk about sampling methods. This is really quite definitional, quite qualitative, and you should just get comfortable with the basic definitions here. This is how you collect your data such that you can get an x bar, and then the inference comes after that about where mu is likely to be. So in order to understand where mu is likely to be, we need to understand how x bar behaves, how it bounces around. And that's where we come across the central limit theorem, which gives us a window into the likely distribution of a sample mean. So it's really important right now that you understand that the sample mean itself is a random variable which bounces around and changes for each sample. In fact, the level to which the sample mean does bounce around, its dispersion, is referred to as the standard error, as we'll see. Okay, and then we can use all of this theory and we can come up with confidence intervals for the true blue population mean. Okay, these colors mean something. True blue population mean. We can say where that likely lives with a certain level of confidence given a sample mean that we have observed and its dispersion, its standard error. Another distribution comes along here that we might be using, the t-distribution, and then a brief discussion and revisiting bootstrapping and something else called jackknifing. So this is your hit list. To start off, we're going to go through these sampling methods and discuss what the difference between probability sampling and non-probability sampling is. So probability sampling is where each member of the population has an equal probability of being selected. Your technique, your method means that you're ensuring that. And therefore, you've genuinely got a random sample. There are no elements that you could never sample. There are no elements that are more likely to be sampled than others. You've got an unbiased, nice, random sample. The text refers to a method that gives you this equal probability as random sampling, probability sampling, and even simple random sampling. Okay, so they all come under the same banner according to the text. Now, one way of carrying out a simple random sample is to simply, if you can list your population, like you've got a phone book or something like that, a phone index, you can index your population, 1 to say 10,000, and then you can use a random number generator to decide which member you pick. Now that would be a simple random sample, but that does rely on you being able to index your observations, your population essentially. Sometimes with surveying and sampling, of course, we are asking people as we meet them. So what we might want to do, so we can't index them, we can't give everyone a label. We can't go into a shopping precinct and give everyone a label and then run a computer random number generator and then go and find the person. Oh, who had 204? Let's go and find them. Can't do that. So what you might do is just go and place yourself in the middle of the population and just simply select every 20th person. And that's called systematic sampling, because you're systematically talking to every kth person. In my example, K was 20. So systematic sampling, that should give you a relative, if you do it properly, that should give you a relatively random sample. Now, for ease of accessing data and for cost reasons, for cheap, to maintain a reasonable level of costs, often we don't engage in probability sampling, which technically we should do to use statistics. Often we engage in what's called non-probability sampling, and this is where we don't have an equal probability of picking every population member. So this is where we use judgment with regards to who we ask or what observations we take, and this is to lower cost, maybe to take readily available data, and this might lead, there's a much more risk there that you lead to a biased sample that doesn't properly reflect the overall population. So any statistician would be very keen to keep an eye on any potential biases that pop up in these non-probability sampling techniques. And the other thing that you need to consider is that your population is stationary, and that is that the parameters. When we say parameters here, we're talking about those blue Greek things we're trying to estimate, like mu and sigma, or sigma squared, mu and mean and variance. We've got to be sure that those things don't change over the time it takes us to take the sample, else inference is invalid. This is a key point about statistics. If we're trying to guess where mu is, we can't have mu moving. That's just too hard. All right. So that's like the archery board moving about randomly, and that's not what archery is about, right? If you take that analogy. Now let's have a look at some probability sampling methods. Now you've got to appreciate that when I say probability sampling now, I mean random sampling. I mean we're conducting our sampling in a way such that each member of the population has got an equal chance of being selected. One way of carrying out random sampling to make sure that our sample represents the overall population is something called stratified random sampling. So the idea here is we want our sample to have the same proportions in, say, gender, maybe income, location, education level. These are the crucial determinants of how we tend to vote. And so if you were taking a sample to, poll what the likely outcome of an election is going to be, what the population is going to do, what you might want to do is make sure you've got the same weights for gender, same weights for income levels, location and education levels as the overall population. That's what these strata, that's what we mean by stratified. The strata are these key characteristics, and we're going to make sure that our sample has got the same weight. So, it might be the case that gender is 50-50. It might be the case that, high income, mid income, low income, whatever that split is, our sample's got the same split as the overall population. It avoids us, through our sampling method, it avoids us only talking to elderly, age would be in there as well, by the way, I should point out. It stops us from just talking to, if you're thinking about polling for an election, stops us only getting a sample that's full of old-aged, relatively senior females that are well off and well educated and in a very sort of expensive location, because that's not going to represent the population. So in a more sort of financial application, if we're creating a sample that is supposed to behave like a bond index, if we're trying to track a bond index, but we don't want to buy every bond in the index, then we could say, right, let's take a random sample, but we're going to make sure that our sample has got the same weights as the index when it comes to crucial drivers of return in bond markets, like, for example, type of issuer or sector, like sovereign, like country or company, corporate, duration of the instrument, like whether it's short-term or long-term, and whether the coupon is high or low. If we decide these are key determinants of returns, then we want our sample to have the same weights in these crucial strata. What we then do is that we then select samples from each subgroup in proportion to the size of the subgroup in the population. Okay. So, for example, if 25% of our index is sovereign, long dated, with a relatively low coupon, then we would make sure that 25% of our sample is sovereign, long dated, and with a relatively low coupon. But we do randomly select within those sovereign, long dated, low coupon bonds. Okay, that's the crucial thing. We're still randomly sampling within these strata that we deem to be important. Another way of attempting to make sure that your sample is representative of the population is to use what's called cluster sampling. So once again, it's all about ease of accessing data and cost. We might be able to generate a small sample of our population, but within that sample, we've pretty much got a broad range of people which represent the population. That's what a cluster is. Cluster is a subset of a population which is representative of the overall population. So it's a bit dangerous, this. You've got to be really careful with it, but you could group residents by county or by state if you're talking, if you're looking at the US, and you could assume that any individual state is representative of the population. You've got to be careful with that. That might not be a good assumption. But the idea is we can't go across the whole of America or across all counties in the UK and ask everyone. So we're going to group people into counties where maybe we've got data easily, and we'll assume that each county is representative of the overall population. So you've got rich people there, you've got poor people, you've got educated people, young people, old people, male, female, all these sorts of things. Now, when you've got your clusters, which are supposed to be mini versions of the overall population, if you just randomly pick a sample of clusters and use all the data in those clusters, so you randomly select 3 or 4 counties, say, and then just combine them together to represent your sample, then that is called one-stage cluster sampling. That in itself might be quite costly because there's going to be quite a lot of data in 4 counties if you're looking at how people are intending to vote or what their opinion is on a certain key crucial topic that you're interested in. So to get it a little bit cheaper, you might use 2-stage cluster sampling. So you randomly select clusters, and then you don't use all the data in the clusters. You then take a random sample from each cluster. So you're using less data there, and that should be a bit quicker and a little bit less costly in terms of time and effort. Note, however, that the cheaper method, cluster sampling, may not be as accurate as the other methods, may not be as purely random as the other methods, because each cluster may not be representative of the overall population. That's a point that the underlying curriculum uses. However, these methods that we've mentioned so far are attempts at random sampling. Don't forget you've got non-random sampling or non-probability sampling, where we don't bother trying to use a method that gives each member of the population an equal chance of being selected. And here we might just be going with the data that we have. You might have an internal database and you decide to sample from it. You don't really care whether that internal database is fully representative of the population. It's just convenient to use it. This would be low cost, but serious questions about biased sampling here and whether we're truly taking a random sample. So really question marks over accuracy here. The other thing is you might just select observations that you feel would be good to go into your sample. Once again, you're relying a lot on the judgment of the analyst there. Imagine standing on the street with a clipboard and deciding you've spoken to a lot of people of a certain type, and then you decide to try and find some other people of another type. That's relying a lot on your skill and judgment about what type people are and whether you're correct in judging them that way. Right, now we've been through those basic definitions, we can start talking about the more quantitative side of estimation and inference. Don't forget the big setup to this module. Sampling is all about observing a sample statistic like X bar and thinking what that means. We can see this, the red one, but thinking what that means about our blue true population parameters. Now, first thing we can define is your sampling error. It's common sense, right? Sampling error, of course, is, if you had to define it, the common sense definition is how far away your sample mean is, the thing you've observed, from what you're trying to estimate, all right? So that's your sampling error. And a corollary from the discussion that we've had so far, that accuracy question mark, you're likely to get more sampling error from non-probability methods than you are probability methods, simply because probability methods go more towards giving each population member an equal chance of being selected, of course. What we need to know about, though, in order to fully understand what our sample mean is telling us with respect to our population parameters, is what distribution we are sampling from when we look at X bar. Now, this is a very important point. And, I'd imagine many of you watching this, you maybe met stats early on. And I always remember stats at school. I remember it was a bloodbath. I actually didn't do it. I went the other way. But I remember the people that did it, I think they were the more sort of artistic people. And they thought, well, how hard can, statistics be? We're just kind of like talking about generally averages and things, right? Well, the answer to that is it can be very super difficult and awfully hard if you never make the distinction between a sample statistic, saying it again, because it's important to say again, a sample statistic like X bar, statistic, and the true population parameter. If you never make that distinction, you are dead on arrival when it comes to stats, okay? So let's make sure that we appreciate that what you're looking at with this red X bar, which is a sample mean, is a random variable, all right? It bounces around. Sometimes it will be lower than the true blue mu. Sometimes it will be higher. Hopefully it's not biased in any way. It won't be consistently above or consistently below. It's not, by the way, as we'll see. But we've got to appreciate that this thing bounces around. And how much it bounces around, by the way, is a function of the size of the sample mean. If you think about it, if you make the size of the sample, all right, n, size of the sample, n. If you think about it, if you take the biggest sample possible, which is the population, you hit the population mean on the head when you calculate the sample mean, because you are looking at the population with the biggest sample possible, and there's no dispersion in the sample mean. But of course, that's not practical. As soon as you start taking a smaller sample from the population than the population as a whole, that's when you start seeing X bars that bounce around, and there's a level of dispersion. Now, we can start talking about this sampling distribution. You've got to think that X bar itself has got some sort of average. X bar itself has got some sort of middle central tendency. All right. X bar itself is a random variable with an expected value, if you like, and it's got a certain level of volatility as well. It's very important that you make that jump. Okay. Hopefully it's very near to mu, but it is still bouncing around because it changes sample to sample. That's a crucial point. So to hammer this home, we're going to do an example. We're going to do an example with something that I think is fairly familiar to most people, and that is a single fair die. All right, single dice, if you like. Okay, it's got 6 sides, and there's numbers 1, 2, 3, 4, 5, 6 on the sides. All right, so there's no rockets being designed here when we say that the true population mean, with an equal chance of seeing 1, 2, 3, 4, 5, 6. You could view this as a discrete distribution. There's a 1 in 6 chance of 1, 1 in 6 chance of 2, 1 in 6 chance of 3, and so on. You get a true population mean of 3.5. That's a blue mu. Notice you can't actually roll 3.5. It's interesting, isn't it? The true blue mu average there is actually not achievable. It doesn't have to be for a discrete distribution, but there it is. Now, when it comes to variance, what we're going to do is we're going to say, okay, how far away is that 1 from the mean of 3.5? It's obviously 2.5 below. So square that deviation. How far is this away from the mean of 3.5? It's 1.5 below. Okay, square that and add it up. You remember that the definition of variance is it is average squared deviation from the mean. How far away is that 3 from the mean of 3.5? This 3 here. Well, it's 1/2 below, so add that squared and so on. It's symmetrical, isn't it? You've got 4, which is a half above, 5, which is 1.5 above, and 6, which is 2.5 above. So add the sum of those squares, take the average. Now this is a population variance, so you are actually going to divide through by the population size, all right, 6. Or another way to think about it is there's a 1/6 chance of each squared deviation. So you multiply through by a sixth, okay, and you get 2.92 there. That's variance. You can square root back down to get standard deviation of 1.71. Okay. Now they are the true population parameters, okay? That's why I've written them in blue. They are true blue. They are the things we're trying to estimate, okay, when we take a sample. Now, I know it seems a bit strange that we should take samples when we know the population parameters. Statisticians not going to get paid very much for taking samples and inferring where mu and sigma are when we already know what they are. However, it's useful to know what they are in a kind of a nice familiar setting to then see what happens when we start taking samples. Let's take 5 samples of size 10. All right, so what we're going to look at here is, imagine that you're rolling a die 10 times, all right? That's a sample. That's one sample. Then you do it again and you get another sample, right? Roll the die 10 times and you get another sample, okay? Each time you do this, you do it 5 times. Each time you do this, you can calculate a sample mean, all right? You'll get x bar 1 from the first sample, sort of size 10, x bar 2, x bar 3, all right? I'll make sure I put a bar on those, x bar 3, x bar 4, x bar 5. These are sample means, and we're going to see them bouncing around. We've actually simulated dice rolls here. These were simulated in by a computer. All right, you've got 5 samples. All right, and the first sample is here. You know, it's random. It's been randomly generated, but what we rolled was right here. What we rolled was, in this particular sample, we rolled 2, 1, 6, 3, 1, 4, 5, 5, 1, 2. Okay, take the average of those. You'll get 2.82. That is my first sample mean. Now, don't forget that mu, the true population mean, is 3.5, right? Don't forget that. Mu, the true population mean, is 3.5. Yeah, it's worth writing that on. Well, I've written it on there, okay, but it's worth carrying forward. You know, we're trying to find out information about the true blue mu of 3.5, okay? We take one sample, we get 2.82. That's our best guess at what the true mean is, but it's not very good. It's quite a way away. If you take another sample, you see something a bit closer, 3.64. Once again, randomly rolling a die 10 times, and that's more representative of the population. This one's not bad, x bar 3. This one's a bit high. That one looks high as well, okay? Now, here's the crucial thing. When you take the average of these sample means, there should be a bar there, okay? When you take the average of these sample means, you realize that you get something that's very close to the true blue 3.5, the true blue population mean. If I take the average of those x bars, all right, look at that. The average x bar, should be a bar there, is 3.55, okay? Recall that the true blue mu was 3.5. So it looks like, doesn't it? It looks like in the scenario when we know what the true blue mu is, we know it's 3.5, it looks like whilst x bar is random, that's the point of this exposition, right? That 3.5 there is blue, it's a blue mu, okay? Whilst our x bars are random, they seem to be a bit noisy. I can't remember the exact figures that we had here, but they do seem to be, I think we went quite low with the first one, didn't we? x1, and then x2 wasn't bad, x bar 2. All right, these are sample means. All right, whilst they were missing, on average, they were pretty close. If you like, your average x bar, your average sample mean, was pretty close to 3.5. That suggests we're sampling from a distribution. It suggests we're sampling from a distribution that is centered on the true blue population mean. All right. In other words, our average sample mean is actually the true blue population mean that we are trying to estimate. And that is true. All right, when you take a sample mean, you are sampling an X bar from a distribution that is centered around the true population mean. That's the point of this little dice experiment, okay? That's a crucial takeaway. And the reason that we know this is because of something called the central limit theorem, okay? The central limit theorem applied to our sampling and estimation, which is what we're doing here, says that for any population, so we just did it with dice, which is not normally distributed. That's what's called a uniform distribution. When there's an equal chance of 6 different things, that's a uniform distribution. For any population, doesn't have to be normal, with a mean of mu and a variance of sigma squared, as the size of the random sample gets large. In other words, we'll talk about what large means for n in due course. But when you've got big enough n, big enough data, enough data, the distribution of sample means, that distribution of X bars, where most of the time we're in the middle, sometimes we get a low one, sometimes we get a high one. The distribution of sample means is approximately normal, okay, with mean of mu, the true blue population mean, all right? And actually we know the dispersion as well. And you're going to have to bank this one. The dispersion, the variance of this X bar as it bounces around the true blue mu in the middle there. The dispersion is related to the sample size. The bigger your sample size, the lower the dispersion of the sample mean around the true blue population mean. Okay? In fact, it's a direct relationship. The variance of X bar is sigma squared, the true population variance, divided by your sample size. Okay? Now you need to know this. This is real need to know stuff. Okay? For any population with a blue mu and a blue sigma squared, when we take an X bar, we know we're sampling from with big enough data, we're sampling from a relatively normal distribution with a mean equal to the true population mean. In other words, the average X bar, the average sample mean, is the true blue, say 3.5 in our dice example, and the dispersion of this sample mean, all right, how much it bounces around. Think standard deviation, all right, the dispersion, well, its variance is sigma squared, the true blue population variance, sigma squared over n, okay? So you need to know. And the fact that we use this central limit theorem to inform us what distribution we are sampling from when we take a sample mean, right? This is the distribution of sample means, okay? This red curve here, the distribution of sample means. Okay, the fact that we've now got this this theorem as part of our toolkit means we can look at an X bar and say, okay, that's a pretty good guess at what mu is, because on average it's right, but there's a bit of dispersion around mu that we need to account for. And guess what? Given that we know our key distances for a normal distribution and confidence levels, we can use those from a previous model to start talking about having a certain level of confidence that the true blue mu is within a certain distance of an X bar. Okay, that's sampling theory. We're there now, we're about to do it. Now we don't often use variance in our analysis. Notice that this technically here is the variance of X bar. Variance, of course, is in squared terms. We're not going to use variance a lot. What we're going to use is the square root of that and treat that like a standard deviation measure. Now, when you take the square root of that variance of X bar, all right, you get back to the standard deviation of the distribution of sample means. So it would be not sigma squared, but just sigma, and not over n, but over root n. Okay. This standard deviation of x bar gets a very special name. It's actually referred to as the standard error of x bar, the sample mean. Okay, because if you think about it, a standard deviation is how far on average you are away from a mean. Well, guess what? X bar being away from its mean, true blue mu, is sampling error, isn't it? We defined that earlier. So if you're looking at your usual sampling error, you're looking at a standard error when you look at the standard deviation of x bar, the sample mean. Okay, so key point here is if you take the square root of this variance of x bar, take the square root of that, you'll get to sigma over root n, and that's the standard deviation of x bar. However, that gets a special name. All right. If you're comfortable with standard deviation so far, then don't be scared of standard error. It's just a special name for the standard deviation of x bar. All right. And it's calculated as sigma over root n. Technically, that's what it is. Take the population standard deviation, all right, and divide through by the square root of the sample size that you're using, and you're good. Or are you? Well, here's, there might be many of you out there saying, well, hang on a minute, Stuart. If we're looking at an x bar trying to estimate where mu is, it's pretty rich that we can, true blue mu, the population mean, it's pretty rich that we can assume we know what the true population standard deviation is. The chances are, in reality, we won't know this, right? So if you don't know the true blue population standard deviation, which we usually don't, what have you got to use to calculate standard error? Well, of course, you can always look at the sample standard deviation, all right, S. You can look at the sample standard deviation, S, all right, and you should use that in the calculation of the standard error of your sample mean when you don't know the population standard deviation, which is all the time, right? Pretty much. Okay. Now that does have implications. In fact, it's really crucial that you keep an eye on whether you know the true population standard deviation and you calculate your standard error using sigma over root n, which can happen in exam questions, but in real life that's not going to happen very much, or whether more usually you're using the sample standard deviation as an estimate for the true population standard deviation sigma in your calculation of standard error, because that does have implications later on, but we'll come back to that later on. One of the things that we should take away at this stage that the curriculum makes a big point about is that you can see clearly from this relationship, whether you use blue sigma or whether you don't know that and you use red S, which you can always get from the sample, one thing we can clearly see is that as n goes up, the standard error of your sample mean, which you can think of as the dispersion, like a volatility, right, around the true blue mu, it goes down. And that's just really a very technical way of saying if you've got more data, then you're more accurate. Your dispersion around what you're trying to measure is lower. You take bigger samples, you'll find that your sample means are not as widely dispersed around the true blue mu. Once again, take that to its extremity, make n as big as possible, you look at the population, and you calculate the population mean. So there's no error, there's no standard error, right? Zero. Okay. Now you can see that in data. This data here looks, it mimics what happens in the underlying text, but it has been numerically derived looking at the dice data. All right. We know that the true blue mu for a single die is 3.5. We know that, right? If we set up buckets for sample means, right? Because sample means could be as low as 2.1, they could be high as 5.2, right? If we set up these buckets, when we take a sample size of 10, what we know we're sampling from is a distribution that is centered on that true blue mu of 3.5, which is in this bucket here, right? It's in that bucket there. But with n only equal to 10, the standard error of our sample mean, the dispersion of our sample mean, standard error of our sample mean x bar, we do know the true blue population mean and population standard deviation, don't we? We know that the true blue population standard deviation is 1.71. We calculated that earlier. We divide that by the square root of 10 and we get 0.55. All right, so that's why the blue distribution here of sample means, all right, remember it's still x bars that we're looking at. Our blue distribution of sample means is quite broad here. There's a bit of noise in it, so it's not perfectly symmetrical. It's because you've only taken a few samples, all right? When we look at a larger sample size, all right, this is really numerically showing that as your sample size goes up, we get more accurate. The standard error of the sample mean, in other words, the dispersion of the sample mean around what we're trying to estimate, gets a lot tighter, doesn't it? It gets a lot smaller. It's the same population standard deviation of 1.71, which we calculated earlier, all right, divided by the square root of 100. That's your n now. And of course, the square root of 100 is 10. So we're looking at a standard error here of 0.17, which is a fraction of what it was before. All right, it's about 3 times as small as it was before. And that's why our dispersion when n is 100 is a lot lower and we're a lot more accurate. All right. So that's what that graphic is showing us in action. It's showing how as the sample size goes up, as you collect more data, you get more accurate. Your standard errors go down. And what we're really saying in words is that your x bars, your red x bars, miss your true blue mu's by a smaller amount, and you're being more accurate. Now, we've covered a lot of ground in the last few slides, and I find it's good to take a time out at this stage. The crucial question that people often ask, the people that are just about to grasp it but are not quite there yet, they kind of say, in my experience, they would say, I don't really get when you use the standard error and when you use the standard deviation. And then they kind of stare in an opposite direction. So let's address that. Remember, whenever you see the words standard error, don't look out the window, look at it, all right? Standard error is telling you about x bar, which we're using to estimate mu. It's telling us the dispersion of x bar. I always actually label it, the standard error, I always label it as SE x bar. It's the dispersion of the sample mean around the true blue mu. Okay, so to picture what's going on, the standard error is how broadly distributed x bar is around the true blue mu. Okay, how much it's spread around it. That's what the standard error is. Okay, now the standard deviation, of course, there's your standard error. Standard deviation we've been using for a little while now, for a couple of modules. Standard deviation applies to a single observation from a distribution, not a sample. So, it's likely that the underlying distribution here is a lot wider, all right, because don't forget the distribution of sample means has a lower standard error, all right, than the standard deviation of the underlying distribution. All right, it's likely if you took a single observation from this population, then you'd be talking about going certain numbers of standard deviations away from the mean to isolate a certain, like 90%. To get 90%, you have to go 1.65 standard deviations. We've done that already, haven't we? All right, for example, either side of the mean. We can say the same sort of thing with x bar, right? Given the central limit theorem, we can now start saying the same thing. We can start saying, well, if you go 1.65 standard errors either side of the mean, not standard deviations, but standard errors, you can start saying that now. You'll capture 95% of the population, all right? If you go, what that says there is 1.65 standard errors, and that says, 1.65 standard errors, okay? And that's what we're going to start doing. Indeed, you could view, just to be sort of not technical, but just to formally see how these two are related. The standard error, you must know that its definition is technically sigma over root n, so true population standard deviation over root n. You must know that, all right? And if we have a sample size of 1, like one observation, that disappears and your standard error is the population standard deviation, right? In other words, these are really the same thing. It's just that a single observation has got a sample size of 1. So you end up sampling something that's got the standard deviation of the original distribution. Okay? As you increase the sample size, as n gets bigger, you get more accurate with your sample mean about the true blue mu, as we've already said, as we've already seen. So, as I've alluded to here, we can now start using our knowledge from previous module about the normal distribution to start talking about where an x-bar is likely to be. If we know that a true blue mu, which we often don't, by the way, but if we did know that a true blue mu was here, then we know when we observe an x-bar, a sample mean, then we are, 95% of the time, for example, given a standard error of sigma over root n, we'll assume we know sigma, right? That's the standard deviation of x bar here, the standard error. Okay, we know that 95% of the time, for example, we will observe a sample mean x bar that is within 1.96 standard errors this time, not standard deviations, but standard errors of the true blue population mean. Okay, so 95% of the time, we will observe an x bar in this range. We could actually calculate it given the standard error, all right? And 5%, only 5% of the time would we observe, for this true blue mu, only 5% of the time would we observe an x bar, a sample mean that was in this range, in this tail here, or in that tail there. Only 5% of the time would that happen, those extreme sample means, okay? And this is the starting point of coming up with a confidence interval for mu, blue mu, given a red x bar. You see, if we know 95% of the time we're going to observe an x bar that's under the bell here and not in the tail, we know if we take 1.96 standard errors either side of that observed x bar and we put it around the x bar, we will capture mu wherever it is 95% of the time. I'll just say that again. Because our x bar 95% of the time is within 1.96 standard errors of the true blue mu, we know if we take our x bar and put that interval around x bar, 95% of the time we will capture the true blue mu. For example, 95% of the time when I take an x bar, I will capture an x bar, say here, for example. It will be somewhere in this under the bell here. When I plonk my 1.96 standard errors either side of that x bar that I've observed, I know that 95% of the time, if I don't know mu, which is really what is the case most of the time, if I don't know mu, I do know that 95% of the time, if I put this confidence interval around my observed x bar, my sample mean, then I will capture the true blue mu. And you can see the slide, you can see that happening on the slide here. All we've really done is picked up this distance here, this confidence interval, and put it around an observed x bar, which is here. You can see the sampling error was this big this time, all right? That's the sampling error, x bar, that's how much it missed mu. But because we're within this 95% range, when I put this confidence interval around x bar, I do capture the true blue mu. It is in that range. I might not know where it is, but due to the central limit theorem, I know there's a 95% chance it is in that range. If I took another x bar, 95% of the time, I'll be in this range, and so another x bar might be here. Take the same, I'll make it red because my x bars have been red so far. Take another sample mean, x bar, all right? It's here. When I put this same confidence interval around that x bar, do I capture the true population mean? Yes, I do. It's in that range as well, isn't it? When I go plus 1.96 standard errors and minus 1.96 standard errors. I don't know where it is, but I know 95% of the time my x bar is in this range here. Therefore, when I put that range around the X bar, 95% of the time I do reach back and cover the true population mean. And that is the essence of estimation, coming up with these confidence intervals. Okay. Of course, 5% of the time you're going to be unlucky. You're going to get an X bar that is outside of that bell, the middle, right? And it's going to be in the tail. And when you put your confidence interval around it, it's not going to cover the true blue mu. It's not in that range, right? So that's a shame. But that's, I've put a smiley face there because I was thinking about statistician. They don't mind this, right? Because there's only a 5% chance of that that mistake, right? They don't mind it because they know the chances of that happening. That's why we're only 95% confident that when we take any X bar and we plonk this confidence interval around it, we've actually captured the true blue population mu, the true blue population mean. Okay, this only happens 5% of the time. The statistician knows that, so they're okay with this. They know 95% of the time they get an X bar that's within this range. It's close enough to mu such that when you put this range around it, you do capture the original true blue mu. Okay, so to formulate what we've been talking about, if you want to come up with a confidence interval for the true blue mu, where does it live? Well, you are a certain percentage confident that you know where it lives in a certain range if you take the sample mean you've observed and you bolt around that sample mean either side a certain number, a z value, distance associated with the normal distribution, multiplied by the standard error of the sample mean, okay, which is calculated as sigma over root n technically. If you don't know sigma, then you use S over root n, and we'll talk a bit more about that in a moment. So here's our first example. This is a crucial application, though. If you didn't like the discussion over the previous 10 minutes or so, and you just want to smash and grab this, take that away. Just remember that this critical distance is for two tails because any confidence interval goes both left and right. That's what that plus and minus sign is telling you. So this is a critical distance for some sort of confidence level in the middle of the bell with two tails, okay? That's what you can smash and grab here. Now, I find labeling helps. If people labeled things, it would help. So a sample of returns on 16 stocks, that's your sample size, has a sample mean of 3%. So that's your X bar. Population standard deviation is 10%. Well, that's nice. They've told us a true blue sigma there. All right, we don't often have that luxury. What is the 95% confidence interval for the mean return of the universe of stocks from which the sample was taken? All right, so we've got a sample mean. What does that tell us about the true mean of all the stocks in this universe that we're sampling from? So we're going to take our X bar of 3%. We're going to bolt on and take off. Now remember, 95% confidence is with two tails. How far do we need to go? Well, remember, it's not about the confidence level. That can confuse people. It's about the area in the tail. So with two tails, there's 2.5% in that tail, 2.5% in that tail, okay? And so we're going to need to go, under a normal distribution, we're going to need to go 1.96 standard errors to the left and 1.96 standard errors to the right, okay? That's using the normal distribution. They're the crucial distances of a normal distribution that we've used before. So there's your derivation of your critical Z value, 1.96, 95% two-tailed, okay? And we're going to multiply that through by the standard error of the sample mean X bar. Remember, it's defined as sigma over root n, okay? In this particular case, we've got a sigma of 10%, so that's nice and neat. And we've got an n of 16, so root 16 is of course 4. What we've got here is 2.5 lots of 1.96. So it's about 2.5 lots of 2, which is about 5. Okay. So when you add and subtract about 5 to 3, you get minus 1.9% to 7.9%. So there should be a percent sign there. Incidentally, something that's come to mind a couple of times as we've done these early quants calculations, people often ask me, when is it okay to work in percent and when is it okay to work in decimals? And my response to that is, are you worried? If in doubt, put decimals in and you'll get decimals out. Okay, so if in doubt, decimals in, decimals out. You could have easily gone 0.03 plus or minus 1.96 times 0.1 over root 16, and you'd get 0.03 plus or minus 0.049, and then you'd end up staring at minus 0.019 to plus 0.079. They're decimals that are coming out of you from you putting decimals in. Okay, so if you're in doubt about whether to use decimals or percentages, it's percentages that you can't always use. Decimals you can. Okay, apart from when a model has been set up to use percentages, but that's the exception that proves the rule. Okay. All right, this is a very important first pass at a confidence interval. Make sure you can do this. Now, what I've said is that the standard error technically is the true blue population standard deviation divided by root n. All right, that's what we've said. But we've also said we often don't know this. We don't know what that is. So we use S, the sample standard deviation, as a proxy for it. Now you can do that, but it's not without its consequences. Okay, if you use S instead of sigma in the calculation of the standard error, the dispersion of your sample mean, then you are actually looking at an X bar which doesn't follow a perfectly normal distribution. It follows what's called a student's t-distribution. This is a slightly different distribution to a normal distribution, all right? And it pops up most of the time, actually, with your inference, because most of the time you don't know sigma, true blue sigma, and you use S, the sample standard deviation, in the calculation of the standard error, okay? Now they're just calling on the slide here, they're calling the sample standard deviation S little x. That's the same as my S, all right? So this is your sample standard deviation, okay? What I just call S. Now, because we're using the sample standard deviation in our calculation of standard error, do you remember when we calculated sample standard deviation S? It's useful to remember that this is where we divided by n minus 1 because we lost a degree of freedom in the data. Well, guess what? That introduces that idea. Because we've used S in the calculation of the standard error of X bar, we've lost a degree of freedom. And actually, it's these degrees of freedom which drive your t-distribution, because you get different t-distributions for different degrees of freedom, essentially different sample sizes. If you think about it, the more data you collect, the bigger your sample size, the closer this t-distribution is going to be to a normal distribution, because the closer your sample standard deviation is going to be to the true population standard deviation, where the normal assumption applies. Okay, but the key takeaway here is that you should use t-values that come out of a t-table for critical values. Here, same formula as before, we're just replacing that term with t-crit instead of z-crit. All right, and you will find that your t values are very similar to z values. They're just a little bit bigger, representing the extra uncertainty that we've got due to the fact that we're estimating true blue sigma using S in the standard error. Okay, so the student's t-distribution, it is a symmetrical bell-shaped distribution. It's fatter than a normal distribution. It's defined, there's different student t-distributions actually, and as you know, it's defined by the amount of data you've got, technically by the degrees of freedom, n minus 1, your sample size minus 1. And as the degrees of freedom increase, this t-distribution does approach a standard normal distribution. In other words, your t-values and your t-distribution approach z-values and a standard normal distribution as you collect more data. In fact, if we've got enough data, then we can assume that t-values are pretty much the same as z-values, okay? But we'll come back to that in a little bit. A t-distribution table, by the way, is slightly different to a z-table. Once again, you'll be given an extract if you need to use it, okay? But there's it's a little bit different, a t-table. You might remember that a z-table, you put a z in and you got a probability out. With a t-distribution table, it's different. What you're going to do here is you're going to put degrees of freedom in, and you're going to put a level of significance in a tail or in two tails. All right, that's what sets your rows and your columns. So don't forget, your degrees of freedom is n minus 1. So you'll know your sample size. You can essentially take 1 off of your sample size, and that dictates which row you're looking at. And then just think about what sort of confidence interval you're after. If you're after a 95% confidence interval, which has been the default case in a lot of our examples, then you know if we're talking about one tail, there's 2.5% in a single tail here. If we're talking about two-tailed, then there's 5% in both tails. So the column that's of interest here is, I always like to think about a single tail. We're interested in this column here. Let's say I've got, let's say my data set contains 41 observations. Well, my degrees of freedom would be 41 minus 1, which is 40. So I'd be interested in this row here. So I'm interested in this row here for my t-values. What comes out the table here is t-values, not probabilities like before with z-tables. And we're interested in this column. That, of course, leads us to pick this number here, 2.021, as our critical t-value. That's what, these numbers are. They are critical t distances. They are like z-values. They're just distances, the number of standard errors we need to go away from the mean to isolate a certain area in the tail. Okay. Notice as you increase your sample size and therefore your degrees of freedom, because degrees of freedom are sample size minus 1, we attempt, these t values tend towards our familiar z values. For example, you know that if we had 95%, the z value for 95% under the bell is 1.96 either side. We've said that a few times. If you go down to the bottom of this column, yes, infinite degrees of freedom, we're moving towards that 1.96, which is the z value we knew would be the case with 2.5% in two tails, all right? Or 5%, 2.5% in a single tail, or 5% in both tails, right? Notice how the t values fall. They're originally quite big, and then they fall towards our familiar z values as we increase the sample size. Okay. What's the other one that we know? We know that with 5% in a tail, we know that the critical z value, do you remember this one? Last module, critical z value was 1.65. Yeah, that's what the z is. And as we can see, with 5% in a single tail here, this column this time, we see that the t value falls and it's approaching that 1.6. Technically it's 1.645. We round to 1.65. All right, here. It's falling down to that. But you would always use the t value. If you're given a t table and the number is there in front of you, you should always use the t value for your confidence interval when you've used S in your calculation of the standard error. Now, because the t values approach the z values, z distances, as your sample size gets bigger, there is a convention, if you like, where if n is greater than or equal to 30, we can approximate t values using our more familiar z values. Okay, so this leads to a little flow chart that I always have in the back of my mind when I'm dealing with z's or t's. And this is how I think. I think, okay, when we're calculating the standard error, do I know the true blue population standard deviation? Chances are I don't. All right. So chances are I'm going down this path here. No. If I do, in the unlikely event that I do know sigma, then of course I would use sigma in the calculation of the standard error. So standard error would be sigma over root n, all right? And then we'd use z values. And the central limit theorem would hold here, all right? There is an extra comment about whether the underlying distribution is normal or not, but we'll make that in a moment. When we don't know the true population standard deviation, that's when in the standard error of x bar, we use the S, the sample standard deviation. And that's where we should use t values, right? But there's an extra comment here. This is where our data gets large, our data size gets large, okay? If n is greater than or equal to 30, then you could use z values to approximate. Could approximate t values with z's, all right? So if you haven't got any t values to play with, but you've got a lot of data, then just go with your familiar z values, which you should know off the top of your head. That's yes, n is greater than or equal to 30. If it's not greater than or equal to 30, then you must use t-values, right? So that's my little flow chart in my head. You're calculating the standard error. If you know sigma, that should be blue over there. If you know sigma, then everything's normal and that's fine. If you don't know sigma, then S, now you kind of hear that almost hissing like a kettle. There's a cup of tea that needs to be made, sort of thing. And so you should use t-values. Now, if your data's large, you could approximate using Zs if you haven't got any t-tables. If you're given a t-table, you should use it, all right? And don't go approximating with Zs if you're given t-values to use. And definitely if your data size is small, then you must use t-values. There's no way you can approx because they're too different. T-values and Z-values would be too different. And that's what's being summarized by this table here that appears on the next slide. This table here, it's covering all bases. There's an extra moving part on here. There's an extra dimension here, but it's covering all bases. It's saying if we know sigma squared, technically variance, and therefore we know sigma, then it's Z's all the way, all right? Whether you've got small data or large data, when we've got a normal distribution. Incidentally, if you know the true population variance and standard deviation, and you've got a non-normal distribution that you're sampling from, you do need to have enough data for the CLT to hold, the central limit theorem to hold. The new bit of information that's on this chart is that if you're sampling from a non-normal distribution and your sample size is small, then the CLT doesn't hold. You just walk away, right? Low levels of data and non-normal distributions, the CLT walks away and says, I'm not holding at all here, right? However, if you've got a non-normal distribution and you've got enough data, if you know sigma squared, the true blue population variance, then you're using Zs. You're back in the game using Zs, okay? Because you know your sigma in the standard error, essentially. So that's all fine. We know that if you don't know sigma, then you use S in the standard error, or S squared, square root of S squared. And that's where you must use t-statistics. If you've got little amount of data, you can approximate your t's using Zs. That's what that asterisk means. If you've got a lot of data, incidentally, CLT says you walk away if you've got small sample size and you're sampling from a non-normal distribution. So that table there is the most comprehensive summary of when you use Zs and Ts, but I follow, more often than not, this flow chart gets me where I need to be. And I just have in the back of my mind, if you've got a non-normal distribution and a small data size, you just walk away. Okay, that will get you to the table, essentially. All right, so let's do this. That's the most important thing now, is to actually do this. We've got a confidence interval here when sigma, the population standard deviation, is not known, okay, which is more usually the case. Let's have a look and see what we get asked. We get asked, you get a sample of returns on 16 stocks, that's your sample size. Sample mean of 3%, looks familiar because it's the same data as before. Sample standard deviation of 10%. Now that's a sample standard deviation now, so that's S, not sigma as it was before. Assuming the returns are approximately normal in the underlying distribution, what's the 95% confidence interval for the mean returns of the universal stock from which the sample was taken? In other words, what's our 95% confidence interval for true blue mu? Okay, so you set your confidence interval up as follows. By the way, there's a T table extract here, all right, which gets repeated here. And you set your confidence interval up. It's always X bar, centered on X bar, your sample mean, plus or minus a critical T in this case. Now, to use my flow chart, all right, what have we got here? We've got, we don't know sigma, so we're using S in the standard error. And when we do that, we should use T values. We've got a T table, so we should use the T values essentially. We don't use Zs, and we can't use Zs anyway because we've got small data size, all right, small sample size. So with all that in mind, we're going to use the T table that we've been given. We'll take a critical T distance from the table and we'll multiply through by the standard error, which represents the dispersion of X bar, of course. So we're going to add and subtract the relevant T value times the standard error. So what is the relevant T value here? So what we're going to do is we're going to say that the sample size, you'll remember, was 16. So degrees of freedom is always n minus 1 when you've got one data set like this, one dimension if you like, and therefore we're looking at degrees of freedom of 15. So the row that we're interested in is this one, and then we think about what our confidence level is. We were asked for a 95% confidence interval, there it is, and therefore remember confidence intervals are always two-tailed. The area in a single tail, if there's 95 under the bell, the area in a single tail will be 2.5 in each tail, right? So the column that we're interested in is this one. So that leads us to focus in on that 2.131 there. That's our critical t-distance. And our standard error is going to be s, which was 10%, divided by the square root of n, which is the square root of 16. Okay. So that's 3 plus or minus 5.33, and that gives us essentially minus 2.33% to 8.33%. So you notice that's a little bit wider than the interval that we had before when we based it on z values, because t values are a little bit bigger than z values. Of course, we know the z value for 95% confidence, two tails, is 1.96. T value here was slightly bigger than that, 2.131. Okay, now we're going to finish up here talking about something that was introduced actually in the previous reading. One way to get a measure of the volatility of x bar, in other words, to measure how much it bounces around, in other words, its standard error, is to simply take lots of samples and directly watch how x bar bounces around. This was briefly mentioned in the previous module. We could use computational methods to just take lots of samples and then directly observe the dispersion of the sample mean across lots of different samples. Okay, directly observe it. This process is called bootstrapping, where we take many samples, we resample from a big original historical data set, we keep resampling with replacements, so things that we pick out we put back, all right, and we calculate the sample mean each time, x bar 1, x bar 2, x bar 3, and then we can actually see how broadly dispersed the x bars are and calculate their sample standard deviation, which would represent the standard error of the x bars. And that's called bootstrapping, and like I say, we met it in the previous module. Bootstrapping is slightly different but similar to jackknifing. Jackknifing is where we calculate multiple sample means. Each one is from historical data but with one element removed. All right, so it's really just a way of systematically removing a single observation from your data set to see how your sample mean would vary if one data point was missing. And that's called jackknifing, kind of carving out one data point, but repeated resampling by removing different data points each time. Your sample mean will bounce around when you do this jackknifing, and you can once again measure the dispersion of the sample means that you observe and use that as a proxy for your standard error. So let's wrap up by looking at an example that's in the curriculum of bootstrapping. So there's a lot of data here, but pay attention to the columns. This is our original data, all right? And what we're going to do is we're going to bootstrap this. We're going to keep sampling from it with replacement. So here's our first resample, if you like. It's a sample drawn from this data where we replace items if we pick them. So for example, the first thing we pick is that thing, 0.055. That comes into our new sample. And then we pick minus 0.033. All right, then we pick 0.255. Now, if you didn't replace these items, you'd just end up picking the original sample, wouldn't you? Because it's the same size. However, notice we pick minus 0.033 again. See that? Because we replaced it into the original data set. We don't pick it out and remove it. We pick it out and then replace it, put it back in. Keep doing that. Look, we pick 0.255 a second time as well because we replaced it. So here's your first resample by doing that for the original data. And this, the mean of these, the average of those is your first sample mean, your first resampled mean essentially. Now do that again, you'll get this resample and you can calculate an x bar 2. Do it again, x bar 3 can be calculated as an average of all these numbers coming out of this original sample with replacement, and so on. You can do it 1,000 times, get a computer to just do it 1,000 times and you'll get x bar 1,000. So it's the standard deviation of these sample means that you're going to use as an estimate for the standard error of x bar, the dispersion of x bar. Okay, so what we've seen here is across our 1,000 samples, you know, we've looked at x bar 1 to x bar 1,000. We've seen these 1,000 sample means, resample means if you like. The average of these sample means is minus 0.01367, that number there. You get told that the sum of the squares of the differences between each sample mean and the average across all resample means. So that's really just your squared deviations, the sum of all your squared deviations, how much each individual sample mean is away from the average sample mean. That all adds up to 1.94143. Okay, what you can do is take that sum of squared deviations, divide it by n minus 1. All right, so you've got, 1,000 is your n here because you've got n sample means. All right, and then take the square root, and you're looking at the standard deviation, sample standard deviation of x bar, and that is an estimate for the standard error of x bar, because the standard error of x bar is the standard deviation of x bar. Okay, so if you pump the numbers through that, you come out at 0.04408. Key thing to take away there is you're looking at the actual sample standard deviation of the sample means that come out of the bootstrapping, and that is a proxy for the standard error of your sample mean. Okay. All right, well look, that completes this section. It's a very important section. The most important bit is being able to do your confidence intervals and making sure that you know when to use Z or T. So get practicing on that. That final point there about bootstrapping, bit of a technical point, all right. But the most important thing, the centerpiece of this particular module, is being able to calculate those confidence intervals. So make sure you do lots of question practice there.